We will generate the 16 QAM modulated signal in this video. So our objective is actually the generation of 16 QAM modulated signal. Our objective, we have to generate a 16 QAM modulated signal which is required for transmission over a wireless channel for random binary data. So we would expect to transmit random binary data, and keep in mind we have to implement 16 QAM modulator in Octave today. If we observe the signal constellation, you can because we have 16 QAM, so we have 16 unique signal points which you can see in this diagram. This is in figure 1. You can see the binary data bits to symbol mapping, right? So you have the these circular points. These actually represent the QAM 16 QAM symbols, and you can see each symbol is associated, or the binary digits are associated with each circle. So this is the QAM symbol which carries 0001 binary data. Similarly, you can see all these 16 unique 16 unique symbols which carry 16 unique groups of binary data, or bits. You can say bits. A binary sequence. It's a representation of ones and zeros. So if you want to, usually our data is in the form of ones and zeros, and if you want to transmit all 4 zeros, for example, our data is 0000, so we would transmit this symbol over the wireless channel. Our next 4 bits may be 1011, so we would transmit this symbol. Now each symbol, if you see, each symbol has two components. For example, this is the symbol which represent 1001, right? So it has two components, a component along x-axis and a component along y-axis, and typically we take this symbol as 1 plus j1, which means that the component along x-axis is 1 and the component along y-axis is also 1. So this point actually in the Euclidean space would be 1, 1, right? This would be the coordinates for this point, or you can say 1 plus j1. Similarly, you have this point which is now x-axis is 3 units. This one is 3 units, 3 plus j1. So x-axis, this is 3 units, while the vertical axis is 1. Similarly, for this point which represents 0000, this point, the coordinates are 3, 3. So on x-axis you have 3 units, y-axis 3 units. So 3 plus j3, it is usually written as 3 plus j3. Similarly, you can find the coordinates of all these symbols. So I would like to concentrate on this symbol and this symbol, and I would generate the code that would be able to transmit these two symbols. If we can write a code for these two symbols, we can also extend it for all the 16 unique symbols. So I will concentrate on writing the code for these two symbols, which can be used to extend for all the 16 symbols of data transmission, because when we have a sequence of ones and zeros, we group it in 4 bits per group. So we can have 16 unique groups, and each of these 16 groups are mapped to the binary. Each of these 16 groups are mapped to symbols, right? 16 QAM symbols, 16 unique symbols. So this is, if you are interested in the theoretical theoretical details of this signal constellation, just go through these the theory which is shared with you in the previous video about the QAM modulator. So today we are going to use the Octave code for implementation. Well, we will actually this is the QAM modulator which we are going to implement using Octave. And if you observe this, our input data is binary data, so we would expect that our data is in the form of 1 zeros, a sequence of ones and zeros, and then we have a level generator which generate two based on this data. Suppose you are getting 4 bits, so for these 4 bits this level generator would generate two components, AI1 and AI2. This is the X component and the Y component, or the value of the X component, the value of the Y component, which goes to these two branches. So the first component goes to the upper branch, the second component goes to the lower branch. Now concentrate on this branch. It's very similar to the QPSK modulator from the like from here onward towards the right side. It's very similar because this the first component is multiplied with the pulse P of t, and that pulse is multiplied with the cosine carrier, right? The cosine carrier, and then we have an orthogonal carrier minus sine of 2 pi fct in the lower branch. So here we get a modulated carrier, modulated in phase carrier, and here we get a modulated quadrature carrier. So we have an in phase carrier and a quadrature carrier. We add them and we get S of t, which is the QAM modulated symbol. So let's see this in the Octave. Actually the tricky part is this one, because the rest these parts we have already covered in QPSK modulation, this part. So we would concentrate on generating these two levels, AI1 and AI2, which actually represent for example, if this is the symbol, so AI1 and AI2 would be 1 and 1. If this is the symbol to be transmitted, AI1 would be 3, which is the component along x-axis, and similarly AI2 would also be 3. So 3 and 3, we would generate 3 and 3 if this bit sequence is to be transmitted. So let's see this in Octave. So I'll go to the Octave and let me start Octave. Okay, let me clear the screen. I would also try to load the, now if you see, I have a list of packages which are installed in the in my Octave. So I need to load the communications package. So because I would need some commands which use this package load communications, right? So it would load a communication package for me, and I can use all the commands available in this package. So let me clear the screen now with the CLC command. Now I would like to open the editor and run this a few commands over here. Now we have this generator. Let me see the image. This is our modulator, right? So let me generate the binary data. We have some binary data. So suppose I want to transmit, let me specifically take some data, and then we would generate a random data, right? So I take the data points here, 1001. So let me take this binary data. I assume that my binary data is 1001. So this is my binary data, right? Binary data, which is 1 0 0 and 1. So for this binary data, I would like to generate okay, it's good practice to start your program with the clear all and close all commands, right? So if you have something in the memory or some opened memory will be cleared with this command, and all the images will be closed with this command. So it's always good practice to start with this one. So this is my binary data 1001, and now I would like to have a function called the level generator, right? The level generator, or let me use this. Well, if you observe, we can have any number of binary. If I have this binary data, I should generate a symbol which has AI1 and AI2. AI1 and AI2 should be 1 and 1, right? So similar, but if I have another symbol, all zeros, then it should give me AI1 should be 3 and AI2 should be 3. So you can use if then else commands, and you can also use the switch command. I prefer the switch command here to choose the symbols. Let me use the switch command, and then we will see how we implement our actually let's implement it as a function. So I would call a function level generator, which I have, and I would give it my binary data, and I would expect that my function should give me two outputs which I can save is AI1 and AI2. I would save it. Now I have to generate this level generator function. It would take input, this binary input, and it would give me output which is AI1 and AI2 based on this input. So let's try to generate. Okay, I'll save this file first. Let me save this file, and I would like to save it as QAM modulator, right? So this is my QAM modulator. Okay, I save my QAM modulator, QAM mod.m, which is QAM modulator. Now I would like to have another function file, which is the new script, or let me say the new function. Let me give the name of the function is LG, right? So this is my new function. Now the function, now I started the new function, and it is already, the syntax is here. We have the function LG, the name which I gave. It has some input parameters, 2 inputs, and it has it would have some output parameters as well, which I would like over here. Instead of retrieval, I would say give me 2 parameters which are A and B. And the input parameter, I have just one input parameter, right, which is just that matrix binary. So I have just one input parameter, and let me call it I1, right? This is my input. It takes my, or let me call it binary data. It takes my binary data matrix, right? So BD is my binary data matrix, one input, and it would give me 2 outputs, right? So if generally speaking, if you call this function with 1 input and 2 outputs, you can always write this. Let's try to run this function first, A, and let me see. I'll tell you how the function works in this simple example, BD plus 1, right? BD plus 1. Now if you see, if you add it, it gives me, if I call this function BLG, which is now available, I'll save this one, and I call my function LG, and I give it okay, it will give me 2 outputs as well, which I need to record in C comma D, 2 variables, and I'll call this function LG. And if I give it 1, right, I give it just 1, see, my C is 1 and D is 2, which is computed here in this function. I pass it a parameter 1, it took that parameter, assign that parameter to A, and add 1 to that parameter and assign it to B, and this A, B are outputs which are A is stored in C and B is stored in D. Now I can see the C and D here in command window. So if you pass some matrix in this one, for example 1, 0 and 1, right, and if I say enter, now I just gave it this matrix as an input, and it gave me two outputs which I store in C and D. So two outputs are the same as I gave it this one, and this is one is added to that input and assigned to one is added to that input and assigned to B, and the B which comes from here I save it in D. So my D is the input plus 1. So this is how the function works in the Octave or in the MATLAB, right? So let me clear the screen. I'll go back here because I have to use the binary data here. So I'll say my binary data comes as a parameter BD in this function. Now what I need to do based on this binary data, I would like to use the switch command. Let me see the switch command, the syntax for the switch command. It is same as the conditional if else, because we need the conditional statement, and the switch statement is an replacement of if then else statement. So I'm now writing here the switch command, right? Switch X. Now what I would do, I would use this syntax: switch X, case 1, case 2, case 3. Let's see, suppose we send this data 1001 to this function LG, it will come to the BD, and now with the switch command, switch BD, let me call it BD, or let me call it X for simplicity, but I have to assign X, I have to let me call it small x, right, not big, let me call it small x, but I have to assign BD to small x. Now it is recognized as small x. Switch command. Now what I'm using this syntax, let me use this case 1. So if my case, if it is 1 0 0 1, I would like to generate my AI. I would like to generate AI1. AI1 is equal to I would like to generate AI1 which is 1, and AI2 is also 1. So, right, so I want to generate these two, and in the end I would assign AI1 and AI2 to A and B. Assign AI1, or I can also replace it here, just say okay, return AI1 and AI2. So it's simple, return AI1 and AI2, right? So it would take the matrix, it would see if it is this one, it would give me AI1 equal to 1, and it would set AI2 equal to 1, and these parameters would be returned by this function. So let's try this simple code, whatever we have done right now, let's try it over here. So if we call this function 1001, what do we get? We get 1 and 1. So this is AI1 which is stored in C, AI2 which is stored in D. So if I make it more meaningful, let me use another AI1 and AI2 here, and it would be more meaningful for you. If you pass this binary data to the function, it would give you two levels, AI1 and AI2, which you can use in the modulator in this modulator, which is shown in this diagram. You can use this. AI1 would be multiplied with P of t. We would generate P of t and the cause function as well. So this is how a simple switch command works. Now we can repeat this code for all the symbols, right? Suppose I try this one for another symbol. My another symbol is I choose this symbol, right? All zeros. My another symbol is this one. So if I pass all zeros, I would like AI1 and AI2 to be 3 and 3, right? So let me choose write the same code, and I would just copy it, and I would say okay, just paste it over here, and if all zeros are input to this function, I would like my AI1 to be 3 and AI2 to be 3, right? Both 3. So let me save this. I save this and now call the same function here to test whether our command works. So when all zeros are passed to this function, it generates the two values, the x component and the y component, 3 and 3. If you pass any other value, for example 0001, it would do nothing because the element 1 is undefined. Now this is undefined in the matrix. It cannot be compared. It is not compared. We have not written code for this one, so it's right now working only for these two bit sequences. You can repeat this code to generate for all the bit sequences of these. For example, this is 1 1, this is 3 3, so this one is 1 3, right? So you have to do it for all these 16 bits. Just repeat it for all 16 bits, and once you repeat this code for all 16 bits, you can use this function. This is the level generator function, and you can call it in your main program. So in the main program, we will call this function, and it would give us these two values. Now what happens now, let me try implement the rest of the modulator part. We have just implemented these two. Now the upper branch, you have to multiply it with t and cos of 2 pi f ct. So we have to let's try to define our frequency. So suppose I take the fc equal to 2 hertz for simplicity, and my time axis. Now I would take the time axis, which is actually our time interval, which is from our signal. Our pulse is from 0 to t, right? Theoretically speaking, our pulse exists from 0 to t, and let's our capital T is 1. So we would have we would generate our samples of our pulse in this from 0 to 1. And suppose I am interested in 200 samples, so I would have a step of 200, and if I do this, now see what will happen. Because I want to I just remove this semicolon so that you can see the output of, okay, change the directory. You would be able to see the output of t. Now if you see the output of t, these are 201 columns, which means, and if you observe it with the whose function, your t is 201. So 201 samples. Instead of 201 sample, I am interested in only 200 samples. So let me start with 1 over 200, and our sample, just I am slicing my time axis in 200 equal parts, right? So if I go to my if I run this whose function again, now I have t variable, which is 200. The time is sliced, 0 to 1 is sliced 200 in like equal slices of 200. Now I would like to generate my pulse p of t. So P of t should be P of t is a pulse which is just unity from 0 to 1. I'm taking just unit pulse, which means I have to generate 200 ones, and if I want to plot my pulse versus t, you can see this code now. I would like to plot my pulse. Let's see whether it is working or not. What happens? Is it working? LG undefined near line number 6, column 16, call from QAM at 6. Okay, it does not recognize LG. I guess it is in the different directory. So our QAM mode is here, LG is not here, so we need to save this LG file, save as LG file, and we want to save it in this directory. Right now it is in this same directory, so hopefully this error will not occur again. So if we call this function, right, we can see that our pulse, the function runs correctly, and our pulse is from 0 to 1. This I have taken 200 samples, right, from 0 to 1, so it is a pulse. This is P of t. We would multiply this P of t with the AIK, right? This is what we is our P of t. It has to be multiplied with AIK and then multiplied with cos of 2 pi FCT. So let's generate the cos 2 pi FCT as well. So this is okay, I'll write in editor. Cos of 2 pi FCT is my psi 1 of t. So this is my psi 1 of t, which is cos 2 pi fc and t. The time axis is from 0 to 1. 200 samples are taken, so it will compute the cos of 2 pi fct for me, and which is psi 1. So this is my cos function. Let's see how our cos function looks like. So let me plot t versus psi 1 of t, and if I run it, this is our 2 hertz, 2 cycles are there for the cos function from 0 to 1. Again, I have 200 samples of this function. Now we generate the upper branch. Now what we can do, we have to generate this signal over here, which is the product of this one and with this one, right? So it's this multiplied by P of t multiplied by cos of 2 pi fct, which is a signal here, and I would call it S. Let me call it S1. So my S1 is AI1 multiplied by P of t multiplied by psi 1 of t, right? So this is my S1. Okay, so we can plot, we can see how S1 looks like, how S1 how x1 this is, let me plot S1 specifically so that we can observe our signal at this instant. So if you see, there is some error again. This operator, non-conformant arguments, OPT, what happened, line 9 column 4. Let's see, line number 9 column 4. Okay, so we have to use the, I guess, the dot multiplication should be used here. So if I use the dot multiplication, it's okay. My program runs successfully. Let me clear it. My programs run successfully, and I got this, which is the multiplication. 1 multiplied by P of t is also 1, and multiplied by cos of t, which is the cos, so we get this signal. So we can get our S1 of t, which is the signal over here, which is the signal at this point. Now let's generate this one, AI2 multiplied by p of t multiplied by minus sine of 2 pi f c t. So the lower one is, suppose this is psi 2 of t, which is minus sine 2 pi f c and t, right? 2 pi f c and t. We can see whether it's generated correctly or not. So let's try to plot the second minus sine versus t. So this is the 2 Hertz sinusoid minus sinusoid from 0 to 1 in the time interval 0 to 1. Now this is generated correctly. Now we have to generate S2. Suppose we call this signal, the signal over here, S2. So it is actually AI2 multiplied by P of t multiplied by psi 2 of t. So let me generate S2, which is actually P of t, multiplied by dot multiplication AI1 dot AI2 dot multiplication with psi 2 of t. So let's see whether this is generated correctly, because we have all ones. So I hope it would be, yeah, okay. So it's generated. AI1 is 1, P of t is 1, in this all 200 samples are 1, and psi 2 of t is 1. So you get this product correctly. Our QAM symbol is the addition of these two, is the summer. So S1 plus S2 would give us the QAM modulated symbol. So if I have S of t, which is actually equal to S1 plus S2, and I would like to plot S of t, my QAM modulated symbol, right? My QAM modulated symbol. So let's see. Now you can see the QAM modulated symbol is not cos, not sine. It is addition of both, and you can see the peak, which is 1.41, right? This peak is 1.41. I will let you know why it is 1.41. And this angle, if you see, this angle is 45 degrees. It's 45 degrees pi by 4, and you can see this from the constellation, signal constellation. This point is at pi by 4, right? And this is 1, this vertical x-axis is 1, y-axis is 1. So this is actually square root of 2. Hypotenuse is square root of 2. So square root of 2 times square root of 2 is this hypotenuse. Square root of 2 is 1.41, and here you can see in the figure that your peak amplitude goes up to 1.41. So this is your QAM modulated symbol, which need to be transmitted over the wireless channel. If you want to transmit 1001 data bits, right? Similarly, you can have you can change this data to 0000, and your another QAM symbol would be generated. Now it works fine. Our code, our logic is correct. So let's try to change the data to all zeros, 0 0 0 0, and let's see what do we get. So we get another QAM symbol which is different than the first one, right? And it is now you can see its peak is a little bit above 4, right? The peak value is 4, so it has a different amplitude, and it has a phase is still pi by 4, and the reason for this phase, these two are at the same phase. This is 3, this is 3, so 3 this should be under the root 3 square plus 3 square hypotenuse, which is 9, no, 3 square, yes, 9, so under root 18. So this is actually equal to under root 18, and you can observe this under root 18 over here. square root of 18. Let's compute square root of 18 in our MATLAB. Let's see, square root of 18 is 4.24, and you would observe this peak to be 4.24. right? So this is the another QAM symbol which is for all zeros. Now what you have to do, this is how you can generate the QAM signal from 0 to t. We have taken the capital T, the time period is 1, and we have taken 200 samples in this period. Now you can repeat this code. You can repeat this code for any binary data, right? Any binary data. You just need to extend these cases. For example, 1001 0000. So you can have other cases which is from here. This, for example, I do it for this one, 1011. So my it would generate AI1 to be negative, and AI2 should also be negative, right? Or let me do another, which one is positive and the other one is negative. Suppose this one. Suppose I do it, or maybe this one, right? So suppose this one, we do it for this one. So we have 0 1 0 1, and x-axis is positive, which is 1. Y-axis is negative, which is -3. So if I want to transmit 0 1 0 1, I would just write another statement, another case, and this is the case 0 1 0 1, and my x-axis is positive 1 and y-axis is -3. So put it -3, right? So if this is the case, now it can work for this symbol as well. So if our data, now let me save it, save this file, and let me call it for 0 1 0 1, right? 0 1 0 1, and if I run it, it would generate the QAM symbol which is for 0 1 0 1. Now you can see this peak amplitude, which is around 3, and this would be this would match this signal. It would match this one. Now the angle is different, right? It's not pi by 4, it's a different angle. We have to see what angle it is. You have the y amplitude is -3, and the x amplitude, the x component is 1. So the hypotenuse is under the root 1 square plus 3 square. So under the root 1 square plus 3 square means square root of 10, right? So if you see the square root of 10, compute the square root of 10. Square root of 10, so it's 3.16, and this peak amplitude, if you see, this should be around 3 point, this should be exactly 3.16, right? This should be exactly 3.16. So this is the third symbol which we have generated. You can do it for all. You just need to copy these cases, right? You just need to copy these 16 cases in the Octave, in the editor of Octave, this LG function, level generator function. Just copy these for all, and then you instead of using this fixed data, you use the random integer to generate a binary data. For example, if I use the instead of using this one, I just comment it out, and instead of using this binary data, I would like to use this one. I would like my battery power should not it should be, I'll insert my battery, but let me use random integer 1, 4. This command can give you 4 bits. So let me put a breakpoint here, and I'll show you how to let me save this one. I would like to put a breakpoint here, right? and let me save this file. If I run it, now you can see the randomly generated binary data in the command window, because I just so this is the randomly generated binary data 0010, but we have not we do not have any function for 0010, so it would not run, right? Our editor cannot run. You just need to use this one for binary data. Let me end it, remove all breakpoints, and let me stop it first, right? And let me do it again. Let me run this one instead of calling it here. Let me run this one in the command window, right? You can now generate the whole 111. Okay, let me say that my binary data, let me see, I would 0101. So this time it gives me 0101, and I have already coded this 0101 0101 here, which is 1 minus 3. So I would like to pass this variable to LG, and I would like to generate AI1 and I would like to store AI1 and AI2. So if you see, it would give me, if I pass this variable to LG, answer is passed to this, and it gives me 1 and minus 3. Now you can see I just passed this to LG level generator, it gave me this value because we have already coded this case. Now you need to code all the cases, right? Once you code all the cases, then your this function would run. Any 4 bits of data would be transformed into a QAM symbol, which is given in line number 13. So hopefully I hope that you can now generate this. You can follow this procedure. You have to generate the random binary sequence using a random integer built-in function in Octave, and implement the level generator using the switch statement. The level generator should generate AK1 and AK2 based on the group of selected 4 bits from binary sequence generated in part 1 according to the bits to symbol mapping as shown in figure 1, right? So you just try to implement it for all the symbols. Implement this 2 branch QAM modulator and show your outputs. Now you have to show the results and the code as well. You have to show the results and the code for your function in your report, right? So follow these steps for the for generating a report. So this is how we generate we implement a QAM modulator using Octave.